All right. So the cryptography challenges start here with password hashes. And as you probably know, MS-DOS used to store passwords in plain text, but ever since Windows came out, it scrambles it with a hashing routine, which is supposed to be a one-way function. And the idea is that even if you're able to steal the password hash, you won't be able to deduce the password from it. Now, the Windows system is a spectacular failure in that regard, but that was the idea. So password has this hash, and since Microsoft does not use any salt, which is where you add some random letters to the password before hashing it, every person in the world who uses password has this same hash, and it's been that way for 25 years. So cracking Windows password hashes is incredibly easy. All you have to do is Google them, and you'll usually find them. However, you can also calculate them. Windows password hashes are incredibly old. They were specified in 1993, which is so long ago, MD5 had not been created yet. So they use MD4, which is ancient and not recommended for any purpose, but Microsoft has not yet updated. So anyway, if you want to do this, you have to add a cryptography library to your Go, and you do that with the command go get, which is very nice. So go get will download a library from golang.org and add it to your Go so you can include this code. So if you want to do password hashes, you can do it with this program. And so I now import this golang.org xcrypto MD4, so I can get even an old, rarely used function like MD4 from a GitHub repository. And now I can execute it here. And so you declare a new MD4 object, and then you write bytes to it, and then you can print out the result, the sum. The reason why hashing does this, in any language you do it, is because all these hashing routines are designed to process data one block at a time. So you could have a huge file that was gigabytes and calculate the hash. You just get a small number of bytes at a time from the file, add them to the hash, and then throw that away to add the next block. That's why you do it in this fashion. Anyway, so that's the function to calculate a hash, and it's called hash1. So I've installed that. And that calculates the MD4 of password. Now, the problem is, if you have been paying attention, it's wrong. Microsoft password, a password on a Microsoft machine hashes to 8846, and here I have 8A9D. So it's wrong, and the reason it's wrong is even though Microsoft's cryptography is incredibly out of date, one thing that is not out of date about Microsoft is their support for foreign languages. Because Microsoft is a commercial product, for a very long time, it has supported foreign languages like Japanese and Chinese and such. So 8 bits for a character is not enough, and it uses an old system of Unicode. Now, Go does not use 16-bit Unicode. 16-bit Unicode was an old way to try to support foreign languages, and it turned out to be a really bad idea because even 16 bits are not enough for all the languages you need. So Go uses something called runes, which are UTF-8, so each character can be as many bytes long as it has to be, 3 or 4, as much as you need, and they're not all the same size necessarily. So I tried for a while to figure out how to get to 16-bit Unicode in Go, and I finally just gave up and did it with brute force by just adding a null byte after each byte. Now, if you have something that's English in ASCII and you want to go to 16-bit Unicode, you just add a null byte after each byte. So this is a nasty, sloppy hack that would work only for plain English passwords, but it will calculate Microsoft password hashes correctly for plain English passwords, not ones that include things like Chinese characters. So that's my hash2. And now it turns my password into 8 runes. And so it has the ASCII for P followed by a null, and the ASCII for lowercase a followed by a null, and so on. So there's the hexadecimal string that's password in 16-bit Unicode, and running that through MD4 gives me the correct Microsoft password hash. So now I can create Microsoft password hashes. And so now you've got some challenges. You can calculate the hash of this password, and now you can crack a hashed PIN. So if you had a 2-digit password, a PIN, you can calculate all the 2-digit password hashes, and then all you have to do is find the hash that contains ADA. See, there are letters in here, BE, AE, because it's hexadecimal. So that's the flag there. Then I have some other challenges here where you get calculate some more Microsoft password hashes, and then you can try other hash routines, MD5 with several rounds. And here's one where you have many rounds of MD5 and many rounds of SHA-1, and you don't know how many rounds of MD5 or SHA-1, and yet it still is pretty easy to do. That's why all these password hash algorithms are extremely bad for passwords, these things like MD5 and SHA, because they're designed to be really fast. So you can calculate the hash of a huge file in a reasonable amount of time. But for passwords, you want the opposite. You want the calculation to be very burdensome so that it takes a long time to calculate a password, like 50 or 100 milliseconds, so that an attacker cannot take a list of 1 million passwords and calculate all the hashes easily. So proper password hashing algorithms like used in Linux and the Mac use 5,000 rounds of a salted password hash, where they add random characters to the password and then run it through 5,000 rounds of something like SHA-512. But Microsoft is still using a very ancient technique that is extremely insecure, and your locally stored Windows passwords are very easy to crack. Anyway, then there's a few other cryptography challenges here I'll just talk about briefly. Here's the Caesar Cipher. And the only thing here is you'll learn how to do a little bit of string processing. So you can take plain text that is ABC, and you can then add it. Convert one character into a byte. So you can have 4IC equal range plain text. This loop will count through every character in the plain text string and put a counting number in I and the character itself in C. You can then convert it to a byte. So now you have byte values of the character, and then you can add something to it. I'm just going to add a key, which is 3. So it's going to shift these things forward 3 letters in the alphabet. This is, by the way, a very sloppy Caesar cipher because X, Y, and Z will move off the letters and turn into symbols, and it doesn't wrap around the way a proper Caesar cipher should, but it will work for simple things. And so that's Caesar1.go. Should be here. Yeah, so you can take ABC, it'll convert it to hexadecimal, 41, 42, 43. Then it'll add 3 to each of those and give you 44, 45, 46. So it gives you a hexadecimal version of the Caesar cipher shift. And all right, so then there's some challenges where you can decrypt things with Caesar cipher. And then you can read from files and output to files. So now that after you learn how to do that, you can then decrypt image files. Image files start with headers, so ping files have to start with .png. So you can determine the key by just trying keys until you get a .png, and so on. So it occurred, I was kind of charmed when I realized this. The Caesar cipher is actually a pretty nice way to encrypt images. Of course, all this is obfuscation. It's not real encryption in that it's very easy to crack. But it does scramble things, so you can't just immediately read the contents. You do have to go through some deobfuscation. This kind of obfuscation is only used by very sloppy cryptography systems written by people that don't understand what they're doing, or by systems like malware. Malware uses a lot of these simple obfuscation techniques because they're really not expecting to hide it from a serious cryptographer. They're just doing it to confuse the malware analyst. And even a little bit of scrambling is often enough to do that. Also, people use this to obscure the code in PHP and web pages just to stop other people from just simply copying your code. And there's a couple of more encryption algorithms here. There's XOR, where you flip the bits one by one. You can do that in Go, of course, easily. So XOR, if the 2 bits are the same, the answer is 0. But if the 2 bits are different, the answer is 1. So if you can take A XOR B, A is this pattern of bits and B is that pattern of bits. So the A XOR B is 3, the number 3, which is an unprintable end of text mark. But capital A XOR small s is in fact printable. It turns into this, which is the numeral 2. Anyway, so you can do that in Go also. Go has the ability to do a simple XOR the same way Python does, just with the up arrow key. So after you convert the key to a byte and a character of plain text to a byte, you can just do an XOR here and then turn it back into a string. So that is XOR 1. And so I have a key, which is S. I have a string, which is ABC. And so the XOR turns into 210, 3 characters. This is single byte XOR, so it's again just an obfuscation technique, not an encryption technique, because the entire key space is only 256 possible values. So it is very easy to break things, to decode things without the key. By just trying all possible keys. And so there are a couple of challenges here where you have to decrypt various forms of files with this. And there's even one here where you use a 2-byte key. So you have to decrypt the first byte with the first 8 bits of the key and the next byte with the second 8 bits of the key, and then you keep reusing them. So it's again just obfuscation, but it does mean you have to try 65,536 possible keys instead of just 256. And the last one I was happy to set up was AES, real strong encryption. In Go, I was able to simplify it to make it reasonable. So you just import this crypto AES library, and now you can encrypt things. If you actually want to encrypt arbitrary messages, you have to correctly add padding to it, and there are various padding systems that do get sort of involved. So here I just worked with blocks that are exactly 16 characters long. So there's my plain text, here's my key, and you can just create a new Cipher object. Remember, I mentioned before, you use an underscore if you don't intend on keeping this value and using it. This is where some error would go, and I'm going to just ignore errors. And so now I make ciphertext equal to this, and I call cipher.encrypt to calculate the ciphertext from the plain text. So it's very simple. And then I decrypted it. So I created a 16-character byte object. There's certainly smarter ways to do it, but I was impatient, so I just created 16 dashes here. That's a way to create an object that's the right size, and then I put the decrypted in there. So this is AES. And so it can take ciphertext like that and decrypt it to high their world. So there's a few challenges where you can practice with that. And the last thing I think I'll mention here, just very briefly, is Rust. Like I say, Go is fast, but Rust is secure. The whole point of Rust is it will not create all the security problems that are caused by C, which is used to write Microsoft Windows and most browsers and so on. Firefox created Rust, and Firefox is written in Rust, and therefore it supposedly will not have memory corruption vulnerabilities. Most of them are not there. So, for example, it does not have integer overflows. If you use C and you have an integer, you can just add numbers to it, and when it rolls over, it will roll over like an odometer. So if you have an 8-bit integer and you add more to it, it will just roll around. Here's an integer overflow in C. So I have an unsigned character equals 230, and then I keep adding more numbers to it. And so it will get 230, 233, 236, and then it will roll over to 2, which is crazy. Why would it, adding a number, make it small again? C programmers get used to this, but it really is a bad thing, and it doesn't happen in Rust. In Rust, if you try to add, you make an 8-bit integer and you add enough, it will just stop and say there's an overflow, instead of rolling over and giving you the wrong value. And the same thing happens with strings. In C, you can define a string and then another string, and you can just put in too long a value in the first string, and it will leak into the second string, which is insane, but that's the way it works. And if you try to do that in Rust, it will not happen. You can examine how they're stored, and what you will see is what should happen. If you put in data that is too long for the string, Rust will reallocate new memory that's big enough and change the pointer to point to the new memory. just like Visual Basic or many languages would. So it is slower and consumes more memory and more processing time, but it does not have this overflow problem where the data in one variable overflows to another. And that turns out to be extremely useful to where Microsoft is in the process, they say, of rewriting portions of their operating system with Rust to try to end. They're certainly looking into that. Microsoft tried for years to deal with their huge security problems by adding special extra libraries and parameters to C to try to decrease the risk of using C. And now they're exploring using Rust. So anyway, that's good, clean fun. Rust fixes almost all the memory corruption problems of C, including dangling pointers and memory leaks. So anyway, that is a summary of the remaining challenges, which you can do. I'm going to stop the recording.